So let us start with the today's topic. We will be studying first about the law of conservation of mass, then the basic law of chemical combination, law of definite proportion, and then law of multiple proportions. So, depending upon experimental data which is collected from various chemical reactions related to the amount of reactants taking part and the amount of products formed, the relation between them, how the elements combine with each other to form a compound, and in what ratio they actually combine. So, this is all studied experimentally and then it is given in the form of these basic laws. So first is law of conservation of mass. So law of conservation of mass is proposed and observed by Antony Lavoisier in 1789. So you know this law from your basic ninth class also, that mass can neither be created nor destroyed. That means in any chemical or physical change you can see that the total mass of the reactant always remain equal to the total mass of products. So let us explain by using certain examples. So you have the two statements here. During any chemical reaction, mass of product is always equal to the mass of reactants. Therefore, the matter, you can say, can neither be created nor destroyed in any chemical reaction. Okay, so you can see this reaction here. This reaction is between calcium chloride, aqueous solution of calcium chloride, and aqueous solution of sodium sulfate. We know calcium chloride aqueous solution and sodium sulfate aqueous solution. In the reactants, you can see from the figure that these are not mixed into each other, but then to bring about a reaction between them, we are mixing them, and once they are mixed they form precipitates of calcium sulfate. So it's a chemical change. So the point which you can note here, this is all experiment, that is before the reaction taking place, that is the mass of reactant is found to be 300.23 gram, and after the reaction took place the mass is found to be the same. So it simply means that in any chemical reaction, the it's only that the matter converts into a different matter, but you know that no new matter is created and already existing matter in the reactant is not destroyed, right? So some new matter, you can say, is formed by the some other combination of reactant species, but the total mass always remains same. So you can have this example. This is a physical change in which water plus some ice cubes are there, right? Say 100 gram, and it is put at room temperature. Okay, so melting of ice starts. It's a physical change, and when it is totally melted and changed into liquid water, the mass is again found to be 100 grams. Okay, so for even for a physical change, it's not that mass is lost. The only condition is that you must keep it in a closed container so that no water is lost due to evaporation. So these are the conditions for the experiment. Otherwise, the uh, whether the mass is lost also, it is in the form of water vapors. Still it has gone to the atmosphere. So experimentally we are not able to find, not able to calculate it, but it is actually not lost somewhere, but it has entered into the atmosphere if it is a open container also. But for measuring the experimental data for the law of conservation of mass, so beta we have to keep the container closed. So this is a simple question. The observation of law of conservation of mass can be best observed when the reaction is taking place. Of course, just now I have told you it should be a closed container so that no matter is, undergo some physical change like evaporation, or it is not lost, so that we can measure it. Okay. So some more examples are there. You can see wood is there, burns in the presence of oxygen to form ashes, the products carbon dioxide gas and water. So according to law of conservation of mass, the total mass of the reactant is equal to the total mass of products. So it is simple. Another example where it's a decomposition of mercuric oxide. Okay, so mercuric oxide is HgO. It when you heat it, it decomposes to mercury and releases oxygen gas. So it is a chemical reaction. So you can see experimental data is available. If you start with 100 gram, you'll get 93 gram of mercury and 7 gram of oxygen. So the total mass on the right side is also 100. So it is proved law of conservation of mass. Now there is some limitation of law of conservation of mass. Law of conservation of mass is actually not applicable on nuclear reactions, right? But so see, the normal chemical reactions which take place in some physical or in some chemical changes where this law is applicable, in those reactions the nucleus of the atom do not take part in any chemical combination. The nucleus remains as such, and we know the entire mass of the atom is actually due to its nucleus. But if nucleus is disturbed, then there is a change in the mass when the reactants convert into products. For example, I have taken nuclear fission here, and one more important nuclear reaction is nuclear fusion. Okay, so in these nuclear reactions, actually what happens, the nucleus of the atom is disturbed. There are certain changes which take place in the nucleus. For example, here, so we will not be going to much detail about these reactions. Just one limitation I wanted to tell you, that when a neutron strikes the nucleus of uranium, then the uranium nucleus becomes unstable and it actually breaks down into two simpler units, that is barium and krypton, and it released three more neutron and lots of energy. So from where this energy came, that is the point to be discussed here. Okay, so actually in these reactions this law is not applicable because there is a difference in the mass of reactants and product, and that difference is called delta M, and delta M is actually mass defect. So mass defect is the mass before minus the mass after, right? So it simply means that mass of reactant minus the mass of products. So here the exact masses are given which are in the AMU scale. Now these masses, if added, this is for the reactant and these are for the products, then you can say there is a little change in the mass, a little difference in the mass, 0.18 AMU. Okay, so if you convert AMU into kilogram, at this stage we do not need much discussion about it because we have not studied AMU scale. Later we'll study it. So it is the only thing which is mentioned here. If you convert this AMU into kilograms, and then using Einstein equation, that is E is equal to mc square, we come to know that this mass is actually not lost, but it is actually converted into energy. Okay, so that energy can be calculated using the formula E is equal to mc square, where c is the velocity of light. So it will be a very large value. Even for a small change in mass, very large amount of energy is released. Okay, so ultimately we actually wanted to study here that the limitation of this law is that it is not applicable for nuclear reactions. There is another important nuclear reaction which is called nuclear fusion. In nuclear fusion, actually some small nuclei of some small atoms, right, they actually combine to form a bigger nuclei. For example, here deuterium and tritium, these are the two isotopes of hydrogen. They combine to form helium, and one neutron is released in this process. So if you see the total mass of the reactant and you see the total mass of the products, these are actual masses on the AMU scale. So you will find here that the mass of products is actually less than the mass of reactants. So when the reactants change into product, there is always decrease in the mass, and that decrease in mass actually converts into lots of energy. So if we combine the law of conservation of mass and law of conservation of energy, then we can make a new statement that in any chemical or nuclear change, you can say even a physical change, mass and energy both remains conserved. If there is some change in mass, then it will appear in the form of energy. Otherwise, in normal chemical reaction where nucleus is not involved, In those reactions, but there are no changes in the mass. Okay, so this is about law of conservation of mass. There is one numerical on this. The numerical says that if 4.2 gram of sodium bicarbonate is added to 10 gram of acetic acid, it is observed that 2.2 gram of carbon dioxide is released. So he's asking about what is the mass of residue. So who is the residue? This carbon dioxide, actually it escapes from the reaction mixture. So who is left? It is sodium acetate and water. You know about this reaction, it's a very simple 10th class reaction you have studied. So we have to find here the mass of this residue. Let the mass of this residue is x. So we'll find here the total mass of reactant. You can see it is 10 plus 4.2, 14.2, and the total mass of product is x plus 2.2. X is residue and 2.2 is carbon dioxide. So here we apply the law of conservation of mass. The mass of reactant is equal to mass of product. So if you apply it, 14.2 is equal to x plus 2.2, you can find x comes to be 12 grams. So this is how you can apply law of conservation of mass. Now we'll come to next is law of constant proportion, and it is also known as law of definite proportions. So what this law says, Joseph Proust proposed this law based on certain experimental observations by him. So what this law says that any given compound always contain the same elements which are present in a particular proportion by mass, means particular fixed ratio by mass. Okay, that is why it is called the constant composition. So let us try to understand it with some example. So here I have given first example is water. Now water can be, you can obtain water from we can talk about any sample of water, whether you obtain from pond water, whether it is a rain water, or it is well water, or is distilled water, sea water, like that. So if water is there, then you obtain from any method or any process or any sample of water, its formula is always H2O. It is fixed. It's not that the pond water have a different formula and well water have a different formula for water. No, in water you see this, right? One molecule of water always contain two hydrogen atom and one oxygen atom. So if the number of atoms are fixed, then obviously their mass is also fixed. For example, we know the mass on the AMU scale. If I'll go for water, then water beta hydrogen is 1 AMU, so 2 hydrogen is 2 AMU, and oxygen is 16 AMU. Okay, so you can say that in water, hydrogen and oxygen are actually present in the ratio 1:8, and this ratio always remains fixed for water. I have another example. It is carbon dioxide. Now you see, I have mentioned here 4 different reactions in which the one of the product is carbon dioxide. So you obtain carbon dioxide by any method, right? But every time carbon dioxide is always made up of carbon and oxygen. It always have carbon and oxygen. The formula is fixed, that is CO2, means it contains one carbon and two oxygen atom. And if we go for its mass ratio, then you can say carbon is 12 and 2 oxygen means 16 into 2, it is 32. So it means that it is always in a fixed ratio, that is 3:8. Okay, so let's move further. Now one question is the simplest whole number mass ratio in which sulfur and oxygen combine in SO2. So we can find it, right? This is SO2. We know sulfur on the AMU scale is 32 and 2 oxygen is also 16 into 2, 32. So the answer is 1:1. So this B is the answer. Okay, so there are certain limitations for law of definite proportion. What is the limitation which is mentioned here? You can see that there are two different compounds. Now this is CH3CO CH3, this is propanone or acetone, you have done in 10th class, and this is an aldehyde CH3 CH2 CHO. both have the same formula actually, if their formula is same. So if their formula is same, you can see their mass ratio will be same. So the limitation here for the law is that different compounds may have the same ratio by mass in which they combine. So that means the ratio which is there for the elements of any compound, it can correspond to more than one compounds, right? So we cannot predict the compound from the ratio. That means if somebody gives you that carbon, hydrogen and oxygen, they combine in this ratio, then you cannot guess the compound. So different compounds may have the same ratio. Why? Because these compounds have the same molecular formula. You can see in both of them 3 hydrogen 6 3 carbon, 6 hydrogen and 1 oxygen is there, right? So actually such compounds are known as isomers. You have studied in 10th class, isomers have same formula. Okay, then another limitation is it's about isotopes. Basically isotopes are what? Isotopes are the elements, atoms of the same element with the different masses, right bete? So you can see we can have two types of carbon dioxide. Now earlier I have told you that in carbon dioxide, carbon and oxygen are always present, in the ratio 3:8. Okay, that is fine when carbon have which isotope in it? Carbon 12, right? So 12 is to 32 is 3 is to 8 beta, right beta? But there is another isotope of carbon which is carbon 14. So you may have a different type of carbon dioxide based upon the different isotope of carbon, that is 14. So the ratio is 14 is to 32. Okay, so this ratio will be different. It is 7 is to 16. So these two ratio are different, but the compound is same, that is carbon dioxide. So when isotopes are to be considered, then we can say it's a limitation of this law. The for same compound the ratio may be different. Okay, so there is one question here for the law of definite proportion. So what this law says, we know that I have told you one basic of this law is that same compound may be obtained from any method. It's the ratio of the combining atom is always fixed. So what did this question says? There is a question where it is copper combining with the nitric acid. This is HNO3. It forms cupric nitrate, and when cupric nitrate is further heated, it forms copper oxide, cupric oxide, and the mass of copper is given to you in the first method, and the copper oxide which is formed is also given to you. So basically the question is talking about two different methods about CuO. In the first method it is actually a product, but in the second method you can read the statement, it is actually the reactant. So in the end the question says that show that this data obeys this law of definite proportion. Okay, so how to solve this now? You can see in the first question, this copper, first of all, when it is heated with nitric acid, changes to cupric nitrate, then it is decomposed, and then it is changes to CuO, right? So you can see that 1.08 gram of copper, actually the same copper is here and the same copper goes here. The rest is the mass of oxygen which is there with copper in cupric oxide. Okay, so can I make a statement here beta that 1.35 gram of copper oxide contains how much copper? The copper with which you have started. Okay, so you started with 1.08 gram of copper, so it contains this much of copper. Okay, so let's find the percentage of copper. Now 100 gram of CuO contain how much copper? Is 1.08 into 100 divided by 1.35, so the answer is 80%. So if 80% is copper, then what is the percentage of oxygen? Because it's only the other element is oxygen, so rest is oxygen. How much it is? 20%. So in the first we have found that copper oxide, copper to oxygen ratio is 80 is to 2, or percentage is 80 is to 20. Okay, so let's see the second method. In second method it says that copper oxide, which is 2.3 gram, when it is treated with hydrogen, it is reduced and it is changed to copper along with water. So the entire copper which is present in 2.3 gram of copper oxide is now 1.84. Okay, so the rest was the mass of oxygen in 2.3, so it is changed to it, that oxygen has gone to water. Okay, so let us see now. Let us find the percentage of copper and oxygen in this. I can make a statement here. 2.3 gram of copper oxide contain how much copper is 1.84. So 100 contains this much, and if you find 100, how much it is the answer? 80% here, right? So oxygen is 20%. So in both the experiments, in CuO, the ratio of the percentage of copper and oxygen is found to be same. So this illustrates the law. Okay, there is another question, and this question talks about copper sulfate crystals contain, one data is given to you already, that copper sulfate crystals, we know copper sulfate crystals are CuSO4.5 water, the crystalline copper sulfate. Okay, so 25.45% of copper is there, and 36.07% is water. And it says that if the law is true, then calculate the weight of copper in order to make 40 gram of crystalline copper sulfate. Right, beta? So we know that in the second line it is also talking about the same compound, beta, copper sulfate की बात कर रहा है, right, which is hydrated. So whether you obtain copper sulfate dot 5 water by any particular method, the percentage of copper is always same. So the first data can be used for the second statement, because both the compounds are same, and of course the percentage of copper will also be same. Okay, so you see here 100 gram of crystalline copper sulfate contains how much copper? 25.45, because its percentage is 25.45. It means if the total compound is 100, then how much copper it contains? 25.45. Okay, so if you want to prepare 40 gram of copper sulfate, then how much copper you require, you can calculate. So it is simply 25.45 divided by 100 into 40. So the answer is 10.18 gram. Let's move further. Now the last topic for the day is law of multiple proportion. So what this law says, it is somewhat different as compared to the other laws, and it's about two elements making more than one type of compounds, right? So what this law actually says, if I just before the statement I'll just tell you, carbon and oxygen, they combine to form two compounds, that is carbon monoxide and carbon dioxide. Hydrogen and oxygen combine to form water and hydrogen peroxide, right? Sulfur and oxygen combine to form sulfur dioxide and sulfur trioxide. So what this law says, see the statement, the weight of one of the element which combine with the fixed weight of another always have a simple whole number multiple ratio, right? So let me make you understand it, then I'll again come back to the statement. Let's see how it works. Suppose I'll take water, better, right, and another compound of hydrogen and oxygen is hydrogen peroxide. Okay, so what we do is, in hydrogen, in water, the ratio of mass of hydrogen and oxygen is 2 is to 16. Okay, and in hydrogen peroxide, again hydrogen are 2, so hydrogen is 1 AMU, so 2 hydrogen means 2 is to 2 oxygen are there, so this time it is 32. So this law says that actually what we have to do, we have to choose one element. Say I choose oxygen, I have to compare, I have to see the ratio of oxygen in this compound, water, and hydrogen peroxide. These two ratio is to be compared against the same ratio of other element, which is by chance it is same here. It is same, that is 2. Okay, so keeping hydrogen same, the oxygen ratio in both the compound is 16 is to 32, which is a simple whole number ratio. Whole number multiple means 16 is 2 times 16, here means it is simply 1 is to 2. It's a simply a whole number ratio. I'll explain another example. Let me take another example of carbon dioxide and carbon monoxide to explain. All right, so let us take carbon monoxide and carbon dioxide. So carbon is 12 and oxygen is 16. Here carbon is 12 but 2 oxygen are there, so it is 12 is to 32. So again by chance carbon is kept same here, which is 12, so you can see the ratio of oxygen is 16 is to 32, means 1 is to 2. So they always means, the law says, I'll just come back to the law now. The law says the weight of one of the element that combined with the fixed weight of another of these element are integral multiples of one another, means the ratio is an integral multiple of each other, right? So suppose you want to keep oxygen same here, oxygen's amount same, and you want to compare carbon, so you have to change this amount of oxygen. It should be same in both cases, so it is 32 here, so you want to make it 32, then it you have to multiply this ratio by 2, so it is 24 is to 32. So now oxygen is kept same, beta, this is kept same, so you just compare carbon in both the compound, it is 24 is to 12, which is a simple 2 is to 1, so it is a simple whole number ratio. So this is your law. So the one last example I have taken for this law is sulfur and oxygen compound. So you see why this law actually says that the ratio of masses of one of the element against a fixed mass of other is a simple ratio, because atoms always combine in whole numbers. For example, in order to make sulfur dioxide, one sulfur combines with two oxygen, right? So that is why here the mass is 32 is to, for two oxygen is again 32, right? And here in order to form sulfur trioxide, one more oxygen joins in that compound, so the here the ratio is 32 is to 48, right? But so again the sulfur is same, that is 32 32, and if you compare oxygen, which is 32 is to 48, which is nothing but 2 is to 3, they are just simple whole number ratio. Okay, so this is law of multiple proportions. So that's all about today's topic, that is we have discussed all the three laws: law of conservation of mass and its limitation, it is not applicable for nuclear reactions. Then law of definite proportion we have done, that is when the elements combine, they always combine in a fixed ratio by mass, their formula is always fixed, you may obtain them from any particular method, right? And the last was law of multiple proportion, which we have just discussed, right? So thank you so much.